Hello everyone. So previously we had discussed on the topic Codeforces, this one strongly connected component algorithm, right? So today we'll be discussing about the topic Kahan's algorithm for the topological sorting. So this is one of the very important algorithms, man. Usually you'll get the chance to implement this algorithm most of the times, right? So let's go step by step. Right, so let's see the definition part first. Let's get into the definition part. So let's see what the definition part say here, right? States here basically in a directed acyclic graph. So if you don't know what acyclic here is, so acyclic graph means basically the graph with no cycles, right? You can just say in the simple terms or in general, a graph with no cycles is called as this one. What do we call acyclic graph? Acyclic graph. Directed graph we know, right? So we'll be having arrow mark in the simple terms basically for the this one directed graph, right? So for the undirected graph, we can consider the both edges. Either you can consider, suppose if you are having like this, so A and B. So this is directed graph, right? So this is going from A to B, right? So undirected graph, we don't have this one basically. We can consider B to A or A to B, right? So this is fine. Acyclic means here a simple example here would be A, B, and C, right? So this is actually without cycles basically. See here, without cycles, we have undirected, uh, this one directed graph without cycles basically. Suppose if we write it like this, so this forms a cycle here or the loop, right? So this is considered as the cyclic graph basically, right? So let me delete this one. Yeah. So in a directed acyclic graph, topological sort arranges the vertices such that for every directed edge u to v, vertex u comes before v in the ordering, right? So again, let me read this one out loud. Just listen to this carefully. In a directed acyclic graph, topological sort, what it does, it arranges the vertices such that every directed edge from u to v, right? From u to v as it is directed, vertex u comes before the v in the ordering, right? So vertex u will be always first, right? So we will be considering vertex u always first before v basically in simple terms, right? So Kahan's algorithm uses in degree, right? In degree in the sense the number of edges directed into the node, right? So the number of edges directed, it is not incoming basically, it's outgoing in degree, right? Towards one node, right? For the B, it has to point to the B. Suppose if we are considering the node B, if it is pointing to node B, then it is considered as the in degree, right? It's out degree in the sense, um, so suppose here, let me tell that itself as well. So this is in degree basically, right? So we are considering for the node A here. So in degree is 1. So for the this one, uh, basically from A, if we are considering the out degree, it is 0. From A to B, it is not going, right? From A to anywhere, we are not considering at all. From B, it in degree is 0. This is not pointing to B, right? So from B, it is going to A. So the out degree of B is 1 here, right? So this is one of the simple examples. Let me delete this one just for the understanding if you don't know, right? So usually I go from the basics or the scratch. Your basics has to be very this one. Basically your basics has to be perfect, right? So Kahan's algorithm uses in degree the number of edges directed into a node and a queue to maintain the processing order, and it uses the queue. Basically, when we are making use of the queue, you would have already guessed that we'll be going with the BFS, right? So Kahan's algorithm I have implemented many times. Basically, for the topological sorting, it uses BFS itself. I'm pretty much sure it uses the BFS, breadth first search, right? So just keep this in mind. This one Kahan's algorithm for the topological sorting uses the BFS, meaning here it uses in degree the number of edges directed into the node and a queue to maintain the processing order, right? And this one BFS uses queue itself, right? Just remember this. Let's move on with the explanation part here. So here the first step is we have to compute, or we will be computing the in degree for each vertex. So I have shown you what is in degree and what is out degree, right? So first thing, for each vertex, what we'll be doing, we'll be calculating or we'll be computing the in degree, right? First step. Then what we will do after computing the in degree for the each vertex, we will push all the vertices with in degree equals 0. We'll push all the vertices, we'll consider all the vertices together. Then we'll push all the vertices with in degree equals 0 initially into the queue, right? So this is very important. In degree with 0, equivalent to the 0 into the queue initially. While the queue is not empty, so this is standardized BFS loop, right? So while of not queue dot is empty, we write, right? Usually, this is standardized, this one BFS loop. Basically we make use of the queue, right? While the queue is not empty, then what we will do, we will remove the vertex from the queue and add it to the topological order. The first this is very important. What we will do while the queue is not empty within the while loop, so we will remove the vertex from the queue, we'll remove the vertex from the queue and add it to the topological order, right? So this is fine for each of its neighbor. First, for each of its neighbors, then we will reduce their int degree by 1. First, what we'll be doing, we will be removing the vertex from the queue and add it to the topological order. But then for each of its neighbor, whatever the vertex that we have removed, for each of its neighbor, we will reduce their int degree by 1. Yeah, this is simple. Now, yeah, let's move on with the third point. If any neighbor's int degree becomes 0, if any neighbor's int degree becomes 0, then again we will add that one to the queue. Then again we will add it to the queue. And if all the vertices are processed, we will get the valid topological order. Otherwise, graph has a cycle. If all vertices are processed, then we'll get a valid topological order. Otherwise, the graph has a cycle, right? The exact same thing what we have discussed in the explanation part. So we will be implementing or we'll be articulating in the form of code or the algorithm with the help of Python programming language. So let's start writing the code for the algo, right? So first, let me go with here from collections. Let me import. What shall I import here? Let me import default dict along with the DQ, along with the DQ, right? So next, let's go with the def. Mm, this one, Kahn, topological, this one, sort, Kahn, topological sort, right? So I'll just go with vertices here. This is fine. Let me go with the edges as well, right? So this is fine, man. Now, within the Kahn topological sort function or the, yeah, function, first step, let's create the adjacency list. Quite obviously, we have to create the adjacency list. That is the reason we have imported default dict as well, right? So I'll just go with here, graph equals default. This is not showing. Right? So this is not DQ, man. We need default dict. That's it. So what's wrong here? Let me write here. Yeah, default dict. Now this is showing. Yep. Let me pass the list here. Right. So now this is fine. Now let's consider edges u comma v in edges basically. One edge to another edge, right? U comma v. So now let me go with graph of u, graph of u. But we have to append the v to u, right? So I'll just go with append. So this is simple, right? So suppose for the example, if edges are 5 comma 0 and 4 comma 0, right? So we are going with 5 to 0 and 4 to 0, right? For this one, graph of u dot append of v, I'm explaining here. This is fine, man. Now let's do one thing. Now let's do one thing. Let's move on with the next step. So next step, within the explanation, we have to compute or calculate the int degree of each vertex, right? So let's do that. I'll just go with here int degree. So let me go with 0 here into vertices, right? Into vertices. Now let's do one thing. I'll just go with for u in graph, for u in graph. So this one for uh, v in graph, for u in graph, for v in graph of u, this is fine. So let me set the int degree of v equals int degree of v plus 1. So this is fine, I believe, man. So here, int degree of I is nothing but the number of incoming edges to the vertex I. So we know this one from the explanation part. Now let's move on with the next step, man. So what will be the next step? Basically, let's move on with the next step, step 3, right? So we are done with the 2 steps. Next step is we have to initialize the queue with all the vertices having the int degree 0, right? So this one, compute int degree for the each vertex we are doing, we have done. So push all the vertices with the int degree 0 into the queue. So let's do that first. Let's initialize the queue with all the vertices having int degree 0. So this one will be queue Uh, let me go with the q equals dq of dq, basically. That's it. Q equals dq. So do we need to go with the dq as well? Yeah, let me do one thing. Let me import dq as well here, right? So this is fine. And now let's write the simple for loop here for u and graph. This is fine. Let me go with one more for loop here for another edge v, right? For v in graph of u actually. Yeah. Now within this for loop, let's keep in degree of v equals in degree of v plus 1. This is fine. Now again, if I want to mention this one, sorry, did I keep wrong? So I'm going completely and so this one I have given same thing here. In degree we have already written. We are already in the step 3, right? Third step actually. We have already initialized the queue. So we are going with the initializing queue with all the vertices having in degree 0, right? Sorry, I got confused, man. So this one has to be for I in range actually. Let me pass the vertices. Let me pass vertices here. This is fine. So within that, we are this one initializing queue with all the vertices having in degree 0, right? So this one here, if in degree of I, if this is equivalent to the 0, then what we will do, let me append here this one. Let me append I to the queue. So sorry, I got confused. Yeah, this is fine. Now let's do one thing. Let's move on with the next step. Nothing but so here this step basically let me tell you one thing. These are starting points, right? So we'll not be having any dependencies for this, right? So we are just going with or we are initializing the queue with all the vertices having in degree 0, right? Don't get confused. Next, let's move on with the next step. Nothing but processing queue. We have to process the queue, right? So I'll just go with so here this one. We have to push all the vertices with the integer 0 into the queue. The queue is not empty. Remove the vertex from the queue and add it to the topological order, right? For each neighbor, for each of its neighbors, reduce their integer by 1. This one. We are going with these parts now. Yeah. Uh, we have to go with this one, right? So let's do one thing. Yeah. Now let's process the queue. So I'll just go with here topological order. Nothing but I'll just give you a topo order. So this one, let me assign this one to the empty array while of q, right? So in the explanation, we have to go with the while loop itself, right? So now let me do one thing. Node equals, let me go with q dot uh, pop left. Let's make use of the pop left. What does the 41 line number 41 indicates? Node equals q dot pop left. We are just taking one vertex with a in degree 0. Next, let's add it to the topological order. How can we order? How can we do that? Topological order dot append. What we need to append here? We need to append node basically, right? So this is fine, man. Now let's do one thing. Let's decrease the in degree of all its adjacent vertices, right? So I'll just go with for uh, neighbor here, for neighbor in graph of node, for neighbor in graph of node. So this is fine, man. Yeah. Now let's set the in degree. Let's set the in degree of neighbor. Set the in degree of neighbor equals in degree of neighbor minus 1. Right. So now what if the in degree becomes 0? Then we have to add the neighbor to the queue, right? So let's write the simple if condition for that. So I'll just go with if in degree of the neighbor, the in degree of the neighbor, if it is equivalent to the 0, value 0, then let's append the neighbor to the or let's add the neighbor to the queue dot append of neighbor, right? So this is fine. This one has to be within the parenthesis. Yeah, we have written within the parenthesis itself, right? So now this is fine. Now let's do one thing. Let's move on with the next step. Let's check if the topological sort is possible or not. So that is the last step, right? So this one. If all the vertices are processed, then we get a topological order. Otherwise, the graph is having the cycle, right? So that part, we have come to the last part. Let's check if the topological sort is possible or not. So let me go with if length length of this one topological order topo order. So if it is equivalent to the vertices, if it is equivalent to the vertices, then let me return here. Let me return. I'll just go with topo order, right? Else what we will do? Else, uh, let's return empty array. Right? Let's return empty array. Nothing but graph has a cycle here. It is not a directed acyclic graph, right? So for that purpose, we'll just return the empty array. So we are done with the what do we call? We are done with the algorithm. So I have explained this one step by step clearly now, right? So now let's do one thing. Let's go with the example graph, right? So example usage. Let me take this one from the Google. Just give me a second here. So let me come here. Let me paste this one. So this is the example. This one will be going with basically. So edges here mentioned, right? So let me draw the graph and let me show you. So here we are going with just actually 5, 5 to 2, right? 5 to 2. This is directed, right? So this is fine. Directed graph basically. And then 5 to 0. And let me go with a 0 here. And then we are going with a 4 to 0. So let me consider 4 here, 4 to 0. Then 4 to 1 actually. Let me consider in this way. 4 to 1. Then 2 to 3, right? So let me consider here this one 3 here. This is fine. 2 to 3. And then finally we have, sorry, let me look into here. 3 to 1, right? 3 to 1 here. This is fine. 3 to 1. So this is the graph they have mentioned. We have considered here, right? So the order we have called here Kahn topological sort function here of vertices and the edges, right? Finally, we are going with the topological order, this one. So this is the graph basically. This is the graph that we are going with, example graph, right? Example will be we are going with, right? So let me explain you step by step. So what we have done here, right? So before running the code, or I have explained this one already, right? So let's go with the example output. So what is the output that we need to get here? Basically, what is the so here topological order would be let me write here 4, 5, 0, 2, 3 and 1. So why the topological order, the output that we need to get here is 4, 5, 0, 2, 3, 1. So accordingly with the example that we have considered here, because see, 4 and 5 have the in degree 0 man. So this one in degree, you can clearly see here. So this is, we have the out degree basically from the 5, but we don't have any in degree, right? So it is 0. For 4 as well as just look into 4 as well. So do we have the in degree? So 4 we have the out degree to the 1 and out degree to the 0 basically. We don't have the in degree for 4 and 5. So 4 and 5 have the in degree 0, right? So both can start first. These two nodes, right? Basically node 4 and node 5, these can start first, these both, right? So removing 4 reduces the in degree of 0 and 1. So if we remove this one entirely, it reduces the in degree of this one. It reduces the in degree of 0 and 1. Will not be 0 will not contain the in degree, and 1 will also not be having the in degree if we remove this one. From 4 itself, we are having the in degree to the 0 as well as the 1. Right? So removing 4 reduces the in degree of 0 and 1. Removing 4, this one, what it does, it reduces the in degree of this one, 0 and 1, right? Reduces the, let me tell here, reduces the in degree of 0 and 1 actually, right? So let me do one thing, reduces the in degree of 0 and 1. Now suppose removing the 5, now we have removed 4. What if we remove the 5? Removing the 5 reduces the in degree of 0 and 2. Suppose if we have removed this one, so from 5 this 2 is having the in degree and 0 is having the in degree from 5, right? So if we remove the 5, this reduces the in degree of 0 and 2. This reduces the 5 actually. Removing the 5 reduces the in degree of 0 and 2, right? So this is fine. Yep. Now 0 and 2 becomes 0 and 2 become 0 in degree, right? 0 and 2 becomes 0 in degree. Now 0 and 2, these are having suppose if you have removed this one 4 and 5, these are having 0 in degree, and this one is also sorry, this 0 and 2 are not having the in degrees at all now. So 1 is still having the in degree. This is coming from 3 basically, right? So this is fine. Now 0 and 2, this part, this is not having the in degree at all. So let me write here in and let me cut this one, right? So this is fine. Now, next step here. So 0 and 2 become 0 in degree. So these are next step, right? So now we have completely removed 5 and 4. So now these are having in degree 0. So this one in degree of the 2 is 0 now. So now we can consider in this way. So this is first step, right? So this is first step, right? So second step here would be 0 and this one 2 are having the in degree 0. Now after removing the 5 and 4, 0 and 2 are having the in degree 0. Now removing 2. So this one. So let's suppose we are deleting 2. Removing 2 reduces the in degree of 1. Removing 2 will reduce the in degree of indirectly it reduces the in degree of removing 2 reduces the in degree of 3 man. Sorry. This one here itself I have written. Removing 2 reduces the in degree of 3. Right. So see this is pointing to this one, right? So removing 2 reduces the in degree of 3 and removing 3 reduces the in degree of 1. Suppose if we have reduced, if we have deleted this one next, so removing 3 reduces the in degree of 1, this one, right? Now, finally, all the vertices are possessed. Now we have deleted this one. What do we call? Removed actually 2 and 3. Now we have removed 2 and 3 successfully, right? So first we removed this one 5 and 4. Next we went with 2 and 0 as we didn't had any in degree, right? So this one now 5 is not having in degree, 4 is not having in degree. After the first step 2 and 0, this is not having in degree. Now we removed 2 and 3. So this will reduce the in degree, this one. So now 1 is also not having the in degree basically, right? So this reduces the in degree of 1, right? After removing 3, this reduces the in degree of 1 as well. Now after this, everything is processed. So this is the second step. So removing 0 actually, removing 2 reduces in degree of 3. Removing 2 reduces the removing 2 actually reduces the uh, yeah removing 2 reduces the in degree of this one. What do we call? In degree of 3. And removing this one, what do we call? Removing 3 reduces the in degree of 1. So this is the second step. So this is first step, this is second step. Then we are only left with 1. Basically removing 3 reduces the in degree of 1 as well. So all the nodes are processed here. So this one also we have considered, all the nodes are processed here, right? So the output that we need to get here is first what we removed, 4 and 5. So accordingly with the first step, first we removed here 4 as well as the 5, right? So this one. So we have given 4 and 5. Then we removed this 2, 0 and 2, 2 and 0, right? Next step. So this one we have written 0 and 2 over here. Finally, we removed 3. So 3 reduce the this one in degree of 1. 3 and then followed by finally 1, right? So 3 1 we have this one written, this one at the end. See here, we have successfully removed first we have considered 4 5, then we removed 0 2, then we removed 3 and 1. So this is the output that we need to get within the array, right? So this is one of the simplest algorithm, only if you understand, right? So implementation will be quite lengthier when it is given in the this one contests and other stuff. It will not look as easier while you are learning. So implementation within the certain time might look might be difficult at that point of time, right? So while learning, while implementing, it will be easier. So while implementing the same thing in the contest within the certain point of time, it might we guys might find this one, right? Tough. That one tough. So it happens to everyone. We are human beings, so not to worry, right? So this is it for the topological sort, Kahan's algorithm for the topological sort. So let me run this one. Let me copy this one entirely. I'll just give a Control J. So let me give a clear screen. Python followed by filename.py. So we are having error. So this one here, uh, expected semicolon, right? And the line number 46. Oh, if condition I have written, yeah. Let me give semicolon here, right? So this one, let me move this one. Right, so this is bit of space is required here, as it shouldn't be equal to the if, right? So we are writing this one within the if condition. Now let me run the same code. So let me give you a clear screen. Yeah. Now see, the output that we are getting here is 452031. 4502 or 203 and 1. this 131. We are getting the desired output, absolute correct output, right? So we are done with the Kahan's algorithm for the topological sorting, right? So this is one of the simplest algorithm if you understand. So this is fine. Now as we are done with the algo, let me summarize whatever we have learned so far so that we can move forward with the this one. What do we call Hungarian algorithm, right? So let me summarize whatever we have learned so far. So there are some what do we call 4 to 5 points that we need to remember here. Just try to remember this one. This is very important. Kahan's algorithm is a BFS based method for topological sorting. So this one I have said while writing the code itself, right? So this is Kahan's algorithm for the topological sorting is a BFS uses BFS basically. Just remember this one, right? So Kahan's algorithm is a BFS based method for the topological sorting, right? So this is fine. Now it works only on the directed acyclic graphs, right? So usually we call this directed acyclic graphs as DAGs. Usually we mention this one by the term DAGs. Just remember this one. While in the question, anyway, if someone is calling DAGs, mentioning DAG is nothing but the directed acyclic graph, right? So whenever you are solving something or you are trying to understand the graph, remember one thing. So you have to know adjacency list and the adjacency matrix, in degree and the out degree, right? Cyclic and the acyclic graph, and you have to know the bipartite graph as well. And you have to know this one. What do we call? Certain algorithms on the graph. So that we are discussing already. So these things you have to know at any cost, right? While you're solving the problems or while you're practicing something. So this is the very basics, right? So these are the primary things, if I want to put it in that way. So you have to know these things at any cost, right? So this is fine. Now again, works only on the directed acyclic graphs. This doesn't work with this one undirected graphs, right? Also cyclic graphs as well. So this can be helpful to this one. What do we call? To find the cycle as well, right? So this is fine. So works only on the directed acyclic graphs, DAGs. Also used in the degree and Q, uses in degree and Q to maintain the order. It uses in degree and Q to maintain order. So that's what we saw in the algorithm. That's what I explained you, right? By considering this example, basically, this part of the example. Yeah. Just now we recently discussed the same thing. So it uses in degree and the Q to maintain order. And the last part here is the time complexity and the space complexity. So the time complexity is big of V plus E. The time complexity is big of V plus E. And what would be the space complexity? The space complexity would be big of V plus E as well. The space complexity would be big of E as well, right? So the time complexity and the space complexity for the algorithm would lead to big of B plus A and big of B plus E respectively, right? So now we are done with the Kahn's algorithm, right? So next we'll be discussing on the topic Hungarian algorithm, right? Hungarian algorithm. For now, this is it. Thanks for watching, guys.